So related to the project, just quick points on the derivation. نتكلم عن كل التفاصيل هذه, how to do the simulation and so on. However, some of you, I think most of you probably are stuck with the derivation of that is required in the derived and simplified expressions for the MA receiver, derived and simplified expression of the average bit error, okay, which is as a function of the average listener. So just quick how to start basically. I gave you basically what the decision regions decision is. You decide for bit 1 when the PDF, the seed signal given S equal 1 is larger than the PDF of the seed signal given S equal 1. What does this mean? So let's see what does this mean. What is the PDF of R given S equal 1? What was R? Yeah, what is it? Gaussian, so what is the mean? In order to have Gaussian, we need two things to know what Gaussian is. Mean and variance. What is the mean given S1? Square root of EB. Given S equal 1, the mean is R is square root of EB plus noise. So R is a noise, which is zero mean, with variance sigma square. And because it's zero mean, I added a constant. So basically R becomes the same Gaussian. However, what is the mean? Square root of EB. Okay? And what is the variance? It's the same variance. Adding a constant doesn't change the variance. So if the PDF of R given S1 is nothing but the PDF of a Gaussian distribution, which is 2 pi square root sigma squared if it is under square root e to minus R minus square root of EB, right? Square divide by 2 sigma square. صح؟ تمام. Everybody's following? Now, what is the other right hand side? Given S equal minus 1, what is the PDF? نفس الشيء لكن ايش اللي فوق؟ The mean. So basically, it's again 1 over 2 pi sigma e to minus over R plus square EB square divided by 2 sigma square. But so now I decide for if the left hand side is larger than the right hand side. I decide for bit 1, so, and I decide for bit 0 if it is the opposite. But so now I just need to simplify this until I get R on one side and whatever solution on the other side. No, it will not cancel. It will not cancel. We have here, when you take the log or the length, this will come on the log, okay? And you will have R squared minus 2R squared of EB plus EB. وبينما هنا هيطلع لك R squared plus 2R EB squared of EB. They will not cancel. So we take the log, simplify. Until you get R larger than whatever threshold. If it is larger, it will be 1. If it is less than, it will be 0. واضح الفكرة؟ What is this threshold? 0. You need to get it. Okay? It's 0 because it makes sense to be 0, but you need to get it. هذا أول شيء. ثاني شيء البروميتر في الأرض. أي سؤال عن هذا؟ طيب probability of error. Probability of error is, I told you that the probability of error is the average, right? Using the total probability log, it's the probability of error given S1 multiplied by the probability of S1, which is half. I told you that it's equal probability, right? Plus the probability of error given S equal minus 1 multiplied by the probability of S equal minus 1, which is again another half. So what you need to find is you need to find the probability of error given S1 and the probability of error given S1. Well, how to find the probability of error given S equal 1. طبعا ده كل ده سنسويه pure 315 has nothing to do with the numbers. لكن probably you are not able to start. So what is this? It's a probability of an event, error event, given a condition. السؤال الآن given s equal 1, what is the error event? هذا error event اسمه error in language. What is it mathematically? Given s equal 1. When do I make an error given s equal 1 in s? When do I make an error given 1 was sent? Yes. Given 1 was sent, the correct is r larger than t. So an error given 1 was sent when r is less than t. So I will make an error. I will commit an error when r إذا r less than t. إيش بسوي أنا؟ إيش هقول إيش؟ البيت كان إيش؟ 0 ولا 1؟ 0. ما حقول إنه 1. So 0 means I make an error. So this is equal to the probability that r is less than t, again given s equal. Do you have H1 and Hadi? So the error in language, we define it into math. Okay? This is the first step. The second step, use the condition. R will have different values depending on what s was, right? So given s equal 1, I know what r is. We use the condition. What is given s equal 1? What is r? Exactly. Square root of EB plus noise less than t. خلاص أشيل الcondition. I use the condition. Now, what is this equal to? أخلي random variable in one side والأي شيء ثاني is another side. Less than t minus square root of EB. I know the distribution of this. This is just use theory. Use the condition in R. R will depend on what S is. So given S equal 1, R equals square root of EB plus N. That's it. For this, you will use the Q function. Okay. Yes. So in order to do this, you need to find what T is and continue. أي سؤال ثاني شباب؟ 3 و 4 تحت. وين؟ find the meaning of يعني ماشي. الآن you need to plot for me signal translation in dB and the bit error rate, right? هذا اللي انتم حيطلع منكم. For every point you will get a point. For every point SNR you will get another. صح؟ You will connect them, you will get a curve. الآن أنا am telling you find the SNR needed to get 10 to minus 4. Let's find it. This will be the SNR. Okay? أي أسئلة ثانية؟ تفضل.
You ask her to generate a uniform number of 1,000 stars. Make it more.
It doesn't matter. It's up to you. This is just for you to guide you. Yes. You can do whatever you want.
And you set the number, right? Repeat and then the number is 1,000.
Yes.
100.
Yes.
If I exceed the number of the cellular and the vector, I will have to change the number of errors.
Yeah, the number of errors 100 is enough. The estimation 100 is enough. يعني هذه 100 ما لها علاقه بال 1000. تفضل.
بالصف الاخير اللي صار 6 انا جربت على دفع البيز صوت التشويش يعني نفسه كل النويز نفس التشويش يعني الصوت نفسه الساوند مع كش لايف
لكن
بس كلهم نفس الصوت نفس التشويش هذا
لا طلعتوا
في شيء غلط يعني
في شيء غلط المفروض انه 0 دي تكون فيري نويز بينما الثاني يكون اقل مرات يمكن لما تطلع يعني اكثر يبي مش تتاكد انه الاس ان ار از ريفلكتد ان يور مش يعني اي اسئله ثانيه wish you all the best in the project you need to work يعني faster than or at least fast so that you don't get stuck in the my Right, so last time we started talking about chapter 7, and in chapter 7 we said that, in chapter 6 we said that we talked or discussed and analyzed and try to understand the random of C's and we define the autocorrelation function and we define the components and the cross correlation function. كلها كانت defined. Now in chapter 7 we try to do the same thing for the frequency. So we try to find what are the frequency contents in a random process. If I have a signal, what are the frequency content? What are the frequency components in a signal? The deterministic signal, control signal. We'll try to do here for a random process. So in order to do that, we need to define a power spectral density. Power spectral density. احنا قلنا when we have a deterministic signal, a typical periodic signal, the frequency content changes with the rate of change. So you have higher frequencies when you have a signal that is changing at a faster rate, right? So for example, the second signal here has a higher bandwidth, requires a higher bandwidth to be filtered compared to the signal above. Yes, then this is the rate of change. Remember, the frequencies are higher compared to here. Similarly, however, in a different way, we try to argue that the autocorrelation function in a random process will be able to give us some information about the frequency content. هنا أخذنا Fourier transform of the signal. What we'll do here, we'll try to argue that if we take the Fourier transform of the autocorrelation function, we'll get what we call as the power spectral density. Power spectral density or power density spectrum. Power density spectrum is basically, it basically gives you very similar information like the PDF. PDF is kind of thing. What information you get from there? What is that? How is the quality one distributed among different values of volume value, right? A power spectral density will give you how is the average power distributed among the different frequencies. Okay. How is the average power distributed among the different frequencies? Now, in order to do that, let's talk about what we call Conserva's theorem. In order to find the average, so this is the average, so the average power. Average power, Pxx. We can, if I don't have a random process, what I do is I take the signal square, right? I integrate for a specific time, and then I take the time to be large. And I divide the length of the time. This is if I have a deterministic signal. If I do have a deterministic random process, then I need to incorporate the expected value, which gives me the average value of the power of the signal. So in order to find the average power of the signal, I need to take expected value of x squared, integrate it from minus t to t, and take t long enough and divide by t. Okay? So this gives me the way the average power is calculated for a random process. This is in time domain. So here, what we do is time domain. Time domain is because we are observing the signal for long enough time, taking the expected value and taking the dividing by t, and basically this gives me the average. Now in frequency domain, we can do the same. أنا ممكن آخذ ال x of t هذه I take for it a Fourier transform. Right? I will get xt of omega. So what I do is I have a random process. I take it from minus t to t. I take this function, I take the Fourier transform. Fourier transform, if I take it, it will be some function, I don't know. Right? If this is x of t, one realization, this will be xt of omega. So simply I take a specific chunk, a specific time segment, I take the Fourier transform, I get xt of omega. Now, if I take xt of omega, I take an expected value, means that I run this for different realizations. Then I divide by 2t and take t to infinity. I consider a very long enough segment, and then I integrate over omega, I will get again the average. So this is in frequency domain. What we do here in frequency domain, calculating the average power, and here in time domain. واضح الفرق يا شباب؟ تمام. What we did here is إذا ما عندنا random process, if you don't have a random process, what do? You take x squared for a specific time, and then you take t to infinity. صح? By this, you get the average power. If I have a random process, I simply need to look at the expected value, which means that I run the experiment many times. So I have this realization, I do this, another realization, I take the average. This is the way I find the average power of random process. Now, in frequency domain, no, I look at one realization, I take its Fourier transform for a specific time. And then I consider t, I observe it for long enough time. Now, when I observe it for long enough time, I will get the xt of omega, which is like the Fourier transform of this realization. I do it for many realizations, so I take the expected value. And then I divide by 2t, take t to infinity, and then I sum over all omegas. This gives me the average. Okay. Now, part of what we did in the frequency domain is what we did is we took the realization from minus t to t, take the Fourier transform, and took t to infinity. So what we did is we observed the random process for long enough time and took its Fourier transform of the square, the square of the magnitude square of the Fourier transform. Now this is called هذه القطعة اللي داخل الحمراء is called the power vector density. PSD. Okay, it's a power spectral density. Now, if I integrate this power spectral density, if I integrate it over omega, if I sum it over omega, different frequencies, I get the power average. تمام. clear؟ يمكن في الواقع diffused. أي أسئلة؟ So very similar to what we did in 207. However, there is an expected value here. What does expected value mean? It means that I do this for many realizations. I take the average. And there is another expected value here, which means that the time domain and the frequency domain, which means that again I do the Fourier transform for many realizations, which means I take the average. هذا الفرق بين deterministic or random process. Deterministic, it's one function, I know it. I take the Fourier transform وخلاص. In random process, no, every time I run the experiment, I get another time function. So I need to run it many times and take the expected value. واللي في الوسط هذه الحمراء is what we refer to as the power spectral density. Power spectral density is a function that tells you how the average power Pxx distributed among the different frequencies. هل معظمها مركز في اللو frequency ولا في الهاي frequency? So that I will be able to process the signal, to filter it, and so on. If I don't know these things, I will not be able to filter the signal and signal process. أسئلة شباب. So the power here is the time average of the second moment. لو تذكروا آخر مرة تكلمنا عن ال A هذا. What was A of whatever inside? It was limit, time average, right? It was the limit as t goes to infinity of 1 over 2t, right? Of whatever. Of the integral minus t to t, whatever. Now, whatever here comes. So this is a time average. This is called the time average. So the average power is the time average of the second moment of your signal. Okay. Now let's move to an example. Probably it will be more clear. So Here we are asking find the average power in the following random process. I gave you this random, which is a typical random process implementation. It's an amplitude multiplied by cosine omega 0 t plus theta. Theta here is where randomness lies. If theta is known, let's start signal having deterministic. It's an amplitude of cosine with known frequency and known phase. However, because the phase is probably a function of a message, it's an FM, a typical FM signal, then the phase itself is a function of your voice. So in this case, the phase is a random process. This makes the whole modulated signal as a random process. So A0 and omega 0 are known, are constants. However, theta is uniform from 0 to pi over 2. Now the question is, find the power of the signal. If the Gödel theta is constant, then what is the power of the signal? A0 squared over 2, right? However, with the randomness, let's see how it will look like. So the whole example is how to find it. So we find the expected value of x squared of 2. Expected value, whatever x squared, just put it here. So x squared is a squared cosine squared omega 0 t plus theta. Now you need to open up the cosine squared, which is half 1 plus cosine double the angle. So it will be a squared over 2 plus a squared over 2 cosine double the angle, double the angle. Now, expected value of a squared over 2, what is it? A squared over 2 because it's constant. So it's expected, the average of a constant is a constant. What about this one? Expected value of a squared cosine 2 pi, omega 0 t. We will just write it as the expected value, which is the PDF multiplied by cosine. Right? To find the expected value is simply whatever inside multiplied by the PDF and integrated over the range of the PDF, right? واضح شباب? So what do we have? We have a squared, a0 squared over 2. And then if we do the integral of cosine, what do we get? Sine? Yeah? Sine? Well, is it sine? Minus sine, okay? And it will be from 0 to pi over 2. You will get basically when you substitute into this. So the expected value of x squared of t is given by a squared over 0, a0 squared over 2 minus a0 squared over pi sine 2 omega 0. Okay? Now, what do you think? Is this a right translation or not right translation? Because the expected value of x squared depends on time. What is the expected value of x squared? It's R of cam. Rxx of 0, right? So you can see that this depends on time, which means that it's not a right translation. Okay. So now, in order to find the average power, you need to take the time average. The average power is the time average of the expected value. So the time average, the time average means that whatever inside, you take it inside. So the time average operator is limit t goes to infinity 1 over 2t integral from minus t to t dt. Whatever inside, it goes inside. So now whatever expected value that we found, we need to put it here and do the integration. What was the expected value of x squared? This one, right? Yeah. So now integrating a squared over 2 from minus t to t and dividing by 2t, what do we get? A squared over 2, right? Now integrating a squared over pi sine 2 omega 0 t from minus 2 to t to t and divided by 1 over t. What do we get? 0. Because it will be sine of 2 omega 0 capital T minus sine of the negative one. And we know that sine will be positive, sine equals minus sine of A, which is basically gives you 0. So we end up with this, which is the same as the average power of the deterministic version of the signal, if theta wasn't there. Okay? You didn't know that before we do this. Okay? Now we could do the same thing here by taking x of t for a specific time. So we can define this for minus t to t. Okay, sure. And take the Fourier transform. If I have a cosine, what is the Fourier transform of the cosine? Right? Now, after that, take this magnitude square, and then the PDF will look like this magnitude square divided by 2t. And the average power will be this magnitude square, which is the ESD integrated from minus infinity to infinity for omega. And if you do this, you will get a square, A0 square. 2/5. Which one? Here? When? Pi over 2. Pi over 2. 2/5. Yeah, why? It's fine. We don't get that. If I look at 0 to pi over 2, right? So it's constant from 0 to pi over 2. Right? And this is the PDF of theta. So what should be the amplitude here? The area under the curve of any PDF should be equal to come. So what is the, in order to get 1, what is the magnitude here? 2/5. Exactly. So 2/5, if you integrate now, you will get 1. Okay, so how do you get good question? Thank you. Fine. So now we know how to find the average power. Now let's talk about the relationship of at the end we need to describe the diagnosis in the frequency so that we are able to filter it and so on. So let's try to understand what is the relationship between the power spectral density and the autocorrelation function. In deterministic signals, we used to get what? The Fourier transform of the signal itself. Right? And this gives me V, which is the Fourier transform of the signal, which gives me the frequency. If I take the magnitude square, it gives me the spectrum, the frequency, the spectrum square. Now, here we don't know the signal. It's not deterministic, so we cannot take the Fourier transform. So what we need to do is, we can measure the autocorrelation function. And if we are able to measure the autocorrelation function, then we're going to the power spectral density. And it turns out that for white sense stationary random C's, the autocorrelation function is the inverse Fourier transform of the power spectral density, and the power spectral density is the Fourier transform of the autocorrelation. Okay? So the power spectral density is the Fourier transform of the autocorrelation function. And the autocorrelation function is the inverse of it, the inverse Fourier transform. How did we do this? It requires standardization. We not do this. What you need to do is you need to know that the power spectral density is the Fourier transform of the autocorrelation function. So نفس اللي كنا نسويه في 7 or T70. If I have a signal, I take the Fourier transform. I know the frequency. Here, no. You don't. If you have a random process, you don't really have the signal, so you cannot take the Fourier transform. But what you can measure is the autocorrelation function. And from the autocorrelation function, taking the Fourier transform will give you the power spectral density, which will give you the frequency quantity. How is the average power distributed on different frequencies? Okay. So the power spectral density gives you how average power distributed among different frequencies. Okay. في الوايت سيستيشن. في الوايت سيستيشن. لكن الآن let's talk about non-white sensation. If we don't have a stationary process, then we can. If we don't have a white sensation, then the autocorrelation function depends on time. صح? It will not be independent of time for the white sensation. So what we can do is take the time average. If we take the time average, it means that we observe the autocorrelation function for long time and take the time average. This will remove the time dependency. And in this case, if we do that, then the power spectral density will be the Fourier transform of the time average of the autocorrelation function. And the time average of the autocorrelation function will be the inverse Fourier transform of it. Wow. In this class, we will mostly always deal with white stationary processes, but at least you need to understand what we need to do if you don't have a white sensation. Any questions, Mark? ذكريات تؤثر بدأت فيكم كده ذكريات مؤلمة. طيب let's take an example. So we have here, we gave you the autocorrelation function. It's a squared over 2 cosine omega 0 time. So first of all, is this a white sensation or not? We don't know the mean, because that you cannot say. Assuming the mean constant, then it's white sensation because it doesn't. The autocorrelation function doesn't exist independent time. In this case, in order to find the power spectral density, you need to take the Fourier transform of this. So this is the Fourier transform of the autocorrelation function. And we know that the Fourier transform of a cosine with the specific frequency is 2 deltas at positive and negative frequency. So if the autocorrelation function keeps oscillating like this, then the ESD will have 2 components at minus omega 0 and omega 0. And in this case, you will be able to you know how to filter in. Okay?
بين كم طالب عشان انتصار 130.
Usually we give you the level. We are not examining you here. إلا إذا كان في تصميم سهل. You can keep it by single. لكن الشيء الواقع ما ناخذ شيء اختباري. Nothing is mathematical. لكن in general, if you need anything in math, you need to have a general. And we are not examining you on calculus or in tourism. We are examining you on concepts of physics. أعتقد هذا واضح في الاختبارات الآن. We never gave you something complicated mathematically. طيب أي أسئلة ثانية؟ Let's have another example. طيب هنا we gave you the autocorrelation function again. It's basically given by this function. If you plot this function, it will look like this. It's maximum at 0 and it decays in a rectangular way to minus t and t, and before that it's basically before minus t it's 0, after minus t, after plus t. What does this give you as information about how the signal is correlated, how the signal moves? And assuming in t, capital T is the bit duration. Assuming t is the bit duration, so the pulse goes from for t, and the next pulse goes for t, the next pulse goes to another t, and so on. What does this tell you? The pulse now and the next pulse, are they correlated? So let me repeat it. Assuming that we have a communication system where we send pulses, every pulse takes 0, capital T as the wave. Okay? So 0 to capital T, into T until T, the next pulse, 2 T until T, and so on. How do you think the pulses from one bit to another bit. And it correlates. The autocorrelation function everything.
Yes.
Yes. Why?
Came from one bit to another bit, and it's not so pulse function.
يعني الآن هذه البلسز 0 T 2 T 3 T. You get pulses, so positive, negative, ممكن negative ثاني, ممكن positive, whatever. Okay. Now, if I look at this is a random process, right? It's a random process. Random process stage, and if I look at it for a specific time, I will see this. If I look at it starting from another time, I will see different bits. So this is 1, this is 0, this is 0, this is 1. If I have different steam bits, I have different bits. So now, the question is, how is this signal in general? It contains, if I do it again, I will get another pulses, How is this signal from here, from this point to this point, from this point to this point? ليش؟
لأن الديريشن اللي 0 غير الديريشن غير البلس.
قصدك البيت. لا أنا أتكلم عن الأوتوكوريليشن فانكشن. How do you know this؟ إيش الأوتوكوريليشن فانكشن؟ إيش يعطيك؟ إيش المعلومة اللي علمها الأوتوكوريليشن؟ How the signal is correlated with itself after tau seconds. So here, after half tau, half t over 2, this is the amount of correlation. Like after t, what is the amount of correlation? So from this point to this point, the signal becomes completely uncorrelated. بينما السيجنال هنا وهنا لا لها علاقة. So the autocorrelation function, this one, tells you that the signal after t seconds, the signal becomes completely uncorrelated with the signal that is delayed by t seconds. Well, similarly in the negative, نفس البوزيتيف يعني تمشي قدام في الوقت ولا تمشي ورا في الوقت. طبعا.
صار نيجاتيف يعني ما نقول انه الى 2 تي correlated
لا انت هنا تتكلم عن السيجنال now دائما تقارن 0 with tau. What is tau? Tau is this is tau. Right? So at least this tells me that this is an autocorrelation function of a signal that after t seconds it becomes totally uncorrelated with itself. Okay. Now, so t is a constant, and the question is find the PST. What is the PST? It's the Fourier transform, right? Now, the Fourier transform, this is rather a simple function. You can just write the function in the rising and multiply it by e to minus j and integrate from minus t to t and write the function in the downward slope and integrate from 0 to t e to minus j omega tau, and combining this will give you a 0 t sinus wave, which is done. Okay. Now let's talk about the effect of t. If I make t large, t large means that the pulse has a larger width. The pulse takes longer time. ايش اللي يعطيك البوزيشن ريت؟ أعلى ولا أقل؟ أقل. And what do you think the bandwidth requires؟ أقل من هذه ولا أعلى؟ أقل صح؟ ليش؟ لأن ال width is larger. Now, if the width is larger, then the autocorrelation function is narrower, صح? Isn't it? Sorry, if the width is larger, the autocorrelation function is wider because t is larger. So let's consider two situations here. Two situations when t large, when t small. T large, what do you have as the autocorrelation function? Well, wide, right? Wide because T is wide, is large. So it will look like this. So this is T, this is minus T. This is the autocorrelation function, isn't it? Now if I take the Fourier transform of this, what do I get? I get the sinc function, right? The scale is sinc function. Sinc function depends on omega 0, omega t, tau. So if you look at this, this will look sinc squared. This will be another function. So this is SXX. But now if I take T small, so T large means what? Means that the pulse duration is very long, which means that the transmission rate is low, as well as the bandwidth is small. And you can see here the bandwidth is small. This is the bandwidth. Okay? And the autocorrelation function is wide. It means that the signal takes time. It's very slow until it changes from one state to another state. Okay? It takes time until it becomes uncorrelated. But you know, if I take T small means what? The pulse is small. It means that the signal changes very fast. So the autocorrelation function will look like this. It's another autocorrelation function. This is T, this is minus T. Right? And if I plot the Fourier transform of this, it will look a wider function. And this will be SXX. So the bandwidth here will be larger than the bandwidth because it changes at faster rate. هذه الفكرة هنا ايش علاقة الاوتوكوريليشن فانكشن بالفريكونسي content of the signal, and how do you know how to filter the signal from the autocorrelation function. Any question? This is a very important concept, and I hope that you get it. Let's talk about properties of the PSD. First of all, the pulse vector density is a density function. What does density mean? First of all, it's positive. Density cannot be negative. You can't have a density of minus 1. Density is always positive. Okay? Also, it's even function because we always deal with real signal. Because of real, we take a transform of the signal, we always deal with an even function. So you never find a PSD that is not even. Also, it's real. You will never get a complex PSD. You can get a complex Fourier transform of the signal. But when you take the magnitude square, the complex part disappears, right? Because you are taking the magnitude square. And we talked about this. The inverse transform of the PSD is the average of the if I integrate the PSD, the area under the curve. So this is area under the curve of SXX. Area under the curve equals the average value. Equals the average. Okay? If I take it's a density function, if I integrate it, I get the area under the curve, I get the average. Now this is just, if I differentiate it twice, I get omega squared SX. This is just one of the properties that you need. طبعا هذه اتكلمنا عنها قبل كده. The relationship for wide sense stationary, the autocorrelation function and the PSD for non-wide stationary, the PSD and the average, time average of the autocorrelation function for a Fourier transform. الفرق في الوايد stationary, the autocorrelation function is not a function. And if it is not wide stationary, it's a function. And because of that, you need to take it down. Let's have question. Now I'm giving you here several PSDs and asking you which one could be a direct or not direct PSD. And after all, given the properties above. So أول واحدة إيش معكم؟ Valid or not valid? Why? It's even. Yes.
I'm not limited.
They're not negative. Cosine is that it goes to negative, right? So this is ايش رايكم valid or not valid? Not valid because of negative. It cannot be negative. What about the other? واضح شباب واحدة? Although it's even, like you've been mentioned, clearly, it's even. It satisfies, it's real, it satisfies all the other conditions, but it's not positive. Yes, the other one. Valid because it's real, it's not negative, positive, and it's even. Okay. Third one. C. Why? Not even. Not even. And probably negative in this. هذه كانت أكبر من هذه تكون. طيب. The last one. Not valid. Why? Yeah, not really. Great. طيب. Let's have another example. Now we have the autocorrelation function given by this. E cosine square omega 0 exponential function of minus W. Now the question is, when E and omega 0 and W are all constant. So this is an autocorrelation function. What do you think? If the mean is constant, is this a White sensation or not? If the mean is constant, is this a White sensation? Mean is constant, autocorrelation function depends on tau, doesn't depend on T, so it's White sensation. Now the question is, find and stitch the power spectral density of X, compute the average power of the low pass part and of the power spectral density, and repeat it for the band pass part. Okay. So let's see. Try assume that omega 0 is much larger than W. So let's see. So this is the autocorrelation function. Now, in order to find the power spectral density, we need to get the Fourier transform. So the Fourier transform of, we have cosine square exponential. So first of all, we need to expand the cosine square as the 1/2 plus half cosine W the angle, and we write the cosine in terms of the complex exponential. Because if we multiply cosine, if we take the Fourier transform of the cosine, it's easier to express it in this because we have exponential. Now, so basically, what do we have here? We have the power spectral density. We'll have what? We'll have a low pass, and we'll have one frequency component at J2x and another one at J minus 2x. So let me write it so that we don't be confused. So Sxx omega is the Fourier transform, right? So what is the equation? What is the Fourier transform? Minus infinity to infinity of the autocorrelation function, right? What is the autocorrelation function? B cosine square exponential. But what is B? We have half plus 1/4 e to j 2x plus 1/4 e to minus j 2x. Right? All multiplied by e to minus j omega x dx. Or d tau. Right?
I think multiplied by 8.
Multiplied by what? By the way, we need to move this like with x should be by tau again. So this is x, we have omega 0 tau. So this will be 2 omega 0 tau, and this is minus 2 omega 0 tau. Yes, where's the b? Multiplied by b? Yes, b. Thank you. There's a b. Thank you. So now we have d tau. So this is j omega. So now we have the Fourier transform of half. What is the Fourier transform of half? Constant. Delta. Okay, so we have delta. Okay, And what is the Fourier transform? What is this? This is e to j 2 omega tau minus j omega tau, omega 0. Omega 0. Okay? So this is the first part, this is the second part, this is the third part. لو تلاحظوا هذه at the frequency of at zero frequency, which is the baseband. This is at which frequency? 2 omega 0, right? And this one at which frequency? Minus 2 omega 0. Okay? And by the way, نسينا شيء اللي هو ما ذكرتوني. لسه في جزء في exponential. Exponential part. So we have exponential of minus W tau, right? And then e to minus j omega tau dt. So we have a low frequency component, let's hold it at low frequency or baseband, and we have positive frequency. Sorry, it's like this way at 2 omega 0, and we have at minus 2 omega 0. Now, if you write this, you will get this. Next time, shall we continue? Thank you very much.